Hello. So, yeah, I'm here to talk to you about a problem that we currently have in the ZK space. In particular, right now, if you want to build a ZK circuit, you have a lot of options. So these are all languages that you could possibly use if you wanted to, start building. However, there's a lot of fragmentation. So you can see that we have external DSLs, which essentially are DSLs that implement custom languages. They aren't, building on top of an existing languages. But we also have embedded DSLs, where people are building on top of existing languages in the form of libraries like Rust, Go, TypeScript, etc. And part of the problem that we have here is they're sharing very little infrastructure. And so typically the way that things work is someone has a particular proof system that they want to take advantage of, and based off of the proof system, they're kind of shoehorned into a particular language. So you can see that there is very little there's very little overlap in the proof systems that are shown at the bottom. However, when you are selecting a language, there's a lot of other things that you would like from the compiler or from the language as well. So these include things like, ideally, you would like to have some sort of constraint optimization to optimize out constraints so you don't have to do hand optimization, which a lot of people here have probably had to do before. It would be very nice to have bug detection tools, so you can rely on auditors like us to find your bugs, but also at the same time, bug detection tools help everyone be safer. And several of these tools have, or several of the languages up there have bug detection tools. And finally, a lot of you who are writing ZK applications are probably very interested in hardware acceleration because you want to make proving faster. And as you can see from this table, there's kind of a lot of variance in this, where all of them have some form of hardware acceleration. However, they often diverge in the type of hardware acceleration that they have, where some accelerate specifically for CPUs, others have GPU support, and so on. In addition to that, only about half of the languages that we're looking at actually have any sort of bug detection utilities. And finally, if we look at constraint optimization, some of them have them in some form. Some of them don't have a whole lot of information about them, which is why Zurgeon says yes, because they do have some optimizations, but very little information about them. And finally, there are others where it's very unclear if they optimize constraints at all, like Plonky 3, which is probably just because it's very new. And so, ideally, we would like to inherit work that people have done in the past, but this isn't really done. And so what are the effects of that? Well, fragmentation can cause a lot of issues. And so in particular, one particular issue that can pop up is compiler bugs, because people are essentially re-implementing the same thing over and over again, from optimizations, hardware acceleration, etc. And so what I've shown here is an example of what I would call a compiler bug. So for those of you who have developed on CIRCOM, you might have heard of this thing called a dummy square, which people use in order to constrain a public input that has no other constraints. And this is because CIRCOM had what I would call a compiler bug, where they would optimize out public signals that were never used in a constraint. And even though this might have already been fixed, I have not been able to reproduce it, people are still adding these dummy squares into their circuits because it's just a known thing, and it's become part of people's normal behavior, even though this is something that ideally would not have popped up in the compiler and is not something that developers would actually need to know. Another side effect that we have is a lot of these ZK languages have very common issues. So if you've seen me in the past, you've probably heard me talk about either tools to find bugs or bugs that are common in a lot of ZK protocols. And you don't have to take my word from it. Here I'm showing a table from a publication that was made in Usenix Security, I believe. And it shows root causes for different applications in ZK circuits. And importantly, they're also looking across different languages. Like, I believe they specifically look across Halo 2 and CIRCOM, but I think that there might be one other. So what do you do about this? Well, typically what people do is they have a common compiler infrastructure. So those of you who are familiar with compilers might be aware of a little tool called LLVM. Probably no one's heard of it. but it's a very popular compiler infrastructure that people use that has many front ends, and it's got many different back ends. And so you compile to LLVM, and then you can produce code for a lot of different machines. And having such infrastructure for ZK can have a lot of improvements. And so that's kind of what I'm here to talk about. We recently got funded for a grant in order to develop this type of infrastructure, which can have a lot of benefits. And so basically I'm here to talk about the IR, the intermediate representation, which is just, it's not a language itself that we expect people to develop, but rather an intermediate language that people can use in order to more quickly build compilers and to specialize compilers in the future. And so in particular, the goal is to allow people to write front ends for any particular language that they want. So what I've shown here are Circom, Zurgen, and Gnark. And then after it goes through the front end, it goes to this kind of intermediate language, which we're working on developing. And we'll take a look at what that looks like soon. The important thing here is once you make it to this intermediate representation, then people can develop independent optimizations, backends, and stuff like that without having to worry about the particular language that someone has created. Like, they don't have to worry whether you're writing in Circom or not. And so this allows us to do a lot of things, which we'll talk about, but these transformations are something that's very common in typical compiler infrastructure. And it also allows us to take that lower level representation and use it in a lot of different ways. So we can use it to generate the witness generator. We can use it to generate different arithmetizations. And finally, we can use it for bug detection, which is the thing that we at Veridise typically do. And so let's take a look at some of the benefits that we can get from this. So once someone has compiled down to LZK, which stands for lower level ZK, they can then go and make use of utilities that other people have written. And people can specialize and write particular parts of that stack without having to worry about the language that someone is operating over. And it can be inherited by other languages in the future, which is the important part, because certain things like optimizations, again, can be shared between languages. And then eventually it will go down to the arithmetization. And once it goes to the arithmetization, then you have basically the constraints in some form, which can again be processed by another utility on the back end. But it just allows more reuse and specialization in these ZK compilers. The other thing that we can do is we can support new language features. So currently we are developing this infrastructure on top of an existing stack called MLIR. And it's not important to know much about MLIR. However, it allows you to create dialects. And the reason why that's important is because as new language features come out, they can be supported via a new dialect, where it essentially just adds support for a new language feature, and people can use that in the future. And so this is very powerful because if you consider, like, I don't know, 4 years ago, when lookups weren't popular, this would not be useful if all of a sudden people were using lookups all the time and this infrastructure couldn't support it. And so the next thing is we're building on something that is extensible so that hopefully in the future, as new advances are made, we can just easily extend the LZK infrastructure to support features without affecting other languages that are building on top of LZK. So let's take a look at what this might look like. So you can see on your left, yeah, you can see on your left a Circom circuit. It doesn't really matter what it does. We'll just kind of compare it to the LZK circuit on the right and get an idea of how things are structured. So first of all, we have a method of expressing subcircuits. And so in Circom, those are templates. And in LZK, they are grouped together as structs. The other thing that you might notice is that when you look at the struct, it includes these declarations in the struct values. So you essentially, when you declare a subcircuit, you have to declare everything necessary in order to essentially witness the computation of that subcircuit. So whereas in SIRCOM you might say this is a component and the body of the template, here instead what we're going to do is we're going to declare everything that's needed in the witness up front so that it's very easy to tell exactly what computation needs to be performed. Okay. There we go. Okay, the other thing that we do is we've separated out the basically witness generation, the compute portion of the ZK circuit from the constraints. And the reason why we do this is because not all languages might allow you to, specify the witness generator. They might have an alternate way of allowing you to specify that. You might, create something separate to fill in the witness, which is provided to the verifier. So you don't actually need to provide both of these parts. And it has other side effects, which I might talk about in the future, or I might not have time, in which case I'd be happy to talk about it more. And then finally, the last part is the constraint part, which obviously what it's going to do is it's actually going to emit constraints, and those constraints are going to be the actual constraints that are included in the circuit itself. So fairly self-explanatory. And finally, the last thing that we have are the inputs. So in this IR, essentially the inputs to the subcircuit are inputs to the compute and the constraint function. So there's some coordination that needs to be performed between compute and constraint because they need to have a somewhat specific signature. Okay, so let's see what this enables. So one thing that we can do here is we can take advantage, or better advantage, of optimization passes. So here what I've shown is the less than circuit, which some of you might have seen in SIRCOM-lib. The important thing here is that there's a critical part of less than which is missing, which is less than assumes that the inputs have already been constrained to be within the range of n. And if they aren't, what it's actually doing is it's checking to make sure that the difference between the two values is within size n, and then it's checking to see the relationship of those two values. And there have been times in the auditing work that we've performed where people don't get this right. They allied the range constraints, even though they are necessary and can have unintended side effects in the circuit, and as a result, programming bugs happen. And so the reason why this is done is, for performance, it's up to the developers to perform the range constraint hopefully once, and that way, there's not a lot of duplication. However, if there are better optimization passes, we can actually take advantage of them to actually make a safe version of the library, which is what's shown on the right. So on the right, what you can see is there's two range checks, which, again, look similar to SIRCOM, which is why they're called num to bits. And including those will allow someone to create a safer library, but also rely on the optimizations to optimize those subcircuit invocations out when they aren't necessary. And this actually isn't very difficult to do because circuits don't have storage. They don't have any way of remembering other values, so they're entirely set by the input values. The input values are what's going to determine the behavior. And so that means that we can easily optimize them out to see by checking to see if num to bits was ever called before on that input value. But this isn't something that's commonly done because there aren't a lot of people who are operating or who are creating these optimization passes, which would be very helpful. And so this can be used to create safer libraries. The other thing that we can do is we can create bug detection tools. That's what Veridise does. And so the next two slides are going to be about easy ways to do that. Some of you might be familiar with some of the tools that we've created in order to identify under-constrained circuits. And this is related to that, where if you have such a representation, you can easily do things like checking the constrainedness of a particular template by simply looking at the constraint function. So here, in particular, you can look at the definition of constrain, and you can see that out is actually under-constrained. And the reason why is because out can be anything if A and B, the two inputs, are 0. And that's because anything multiplied by 0 is going to be 0. And so this is something that we can implement once rather than having to implement for each individual language, which is kind of what we have to do now. The next thing that we can do is we can add in easy static analyses. So at Veridise, we have static analysis tools, but again, they're kind of specific to each particular language, and it would be useful to create static analyses which can be inherited by different languages. And what I mean by static analysis is we're statically looking at the source code to try to identify bugs. And so here you can see, again, a LZK circuit, and we can find a bug very easily. Because if you look at the circuit, you can see that in the compute function that there is an assignment to out right here. But the other thing that you might be able to notice is that there's no corresponding emitted constraint in the constraint function. And so this allows us to do some very easy static analysis where, if we were in SIRCOM, we might look for something like the single arrow. But here, we can just simply inspect the two functions that are provided and look for discrepancies. And this is a common way that static analyses that we've built at Veridise have been able to identify bugs. So that is the information that I have right now about LZK. If this sounds interesting to you, I'd be happy to talk about it or talk further about it or answer questions. It's something that we are currently building, though, and so if you have opinions or any thoughts, talk with us. This is infrastructure that we're currently developing and will be available to everyone. It will be open sourced.
Thanks, Joe. I enjoyed your talk every time.
Thank you.
Any quick questions? Okay.
Hi. Yeah, great talk. I'm really excited that you're using MLIR.
Oh, okay, good. Another MLIR fan.
Yeah, I think one question I have is how far down the lowerings do you currently go to? What do you emit right now?
Yeah, so this is still in progress. We just had the grants accepted. So the current plan in the current scope of the grant, I believe, is that the first supported arithmetization that we'll have is R1CS, and so we'll emit R1CS from the constraints. And then because we're building on top of MLIR, it'll be very easy to translate the dialect to the LLVM dialect, and so people will be able to compile the witness generator through LLVM.
Yeah, I think a really exciting part is that because of MLIR's architecture, you can keep lowering and keep lowering.
Yep.
And that's actually quite interesting to us from Ingonyama because we could potentially take whatever you emit and we can keep optimizing it for specific hardware, and we can just go from the DSL straight to hardware.
And that's part of the reason why we wanted to design this, because I'm sure as you guys try to support different hardware with different languages, you kind of have to go and I guess if you're supporting Rust-based DSLs, then hopefully most of the work you can do in LLVM, but then if you get to any other language like SIRCOM or GNARC, you have to basically rewrite everything. And that's the reason, we had the same problem. And so we could have done something specific for Veridise where we developed this internal representation, but we thought it made more sense to try to provide it as common good.
Yeah, and I think also at the higher level when you're eliminating, for example, zeros, that's also saves a lot of time because when we try to optimize some specific proofs to be accelerated, for example, on the GPU, a lot of times you have big chunks of things that are doing redundant work.
Yeah.
If that's automatically handled all the way down, that would be great.
Yeah.
Thank you.
All right. Thank you, Joe.